we are going to talk about support vector machines. So let's get started. So support vector machines, a brief history here, was invented by Vladimir Wapnick. So basically the idea here is that he wanted to get the benefits of nonlinear models without the drawbacks of nonlinear models, because linear models is always easier to deal with, has better understandability. So could we get those ideas within a model while also having the power of the nonlinear models have? So the three key questions addressed by SVMs, support vector machines is short SVM, which is the best of many possible linear decision boundaries. So remember from the discussion of the perceptron, so if you have, right, like data points like this, then a line would be able to separate them. But then this line is also feasible, this line is also feasible, and so on. By feasible, I mean it does the job, it does separate them. So which one is the best among these? So how can we define that? What's best? Are all labeled data points equally valuable in determining the boundary? So each of these points, are they all equally valuable? Or maybe some of them play a greater role in determining the best boundary? And can we avoid the curse of dimensionality when adding feature combinations? So there's different type of SVMs, and the nonlinear SVM, basically the SVMs that are capable to classify nonlinear cases, is basically adding features to it, right? Taking it to a higher dimensionality. But when we do that, then there's always the problem of curse of dimensionality, because too many dimensions will add more problems to the already existing problem we have. So can we avoid that, or can we at least decrease that amount of problem there? So SVMs try to answer these questions in an elegant way, I would say. So in this example, if we enumerate these lines 1, 2, and 3, which line looks best to you? Although 1 and 3, does the job in terms of separating them, they come, if you put a bit more points here, and let's make these like crosses to make it more understandable here, right? So they come very close. 1 and 3 comes very close to each of the cases here. So although they are good in separating these points, if you assume these are the training points, if I were to get new data points, right? The new data points, let's color them as green. They can be like this, right? They can be like this. So there can be points that are on the other side of these lines in the new testing data, let's say. The same thing for these crosses as well. There might be points here in the testing data. There might be here, and there might be here as well. So you see all these points are now going to be misclassified if I choose either 1 or 3. And this is very plausible because they are very close to either one of the cases there, either one of the classes. But 2 is the best, as you can see, among them, because the 2 is as far as possible from each of the classes, right? There can be still points, in a testing data that comes like this, but there will be very few. Basically 2 is as far as possible from each of the classes, so that's why it's the most safe one, right? It's the most safe one compared to 1 and 3. So that's the solution of SVM. SVM tries to find that line that is as far as possible from each of the classes in your data set. So what SVMs does, okay, I need to get rid of these points here. All right, good. So it finds the decision boundary with the largest margin given, which gives the best solution. Okay, this distance between the two classes is called the margin, and what SVM is trying to do is maximizing this margin. The other name for support vector machines is also referred to as the large margin classifier, right? The large margin classifier, because SVM is not only satisfied by classifying the different points correctly, it tries to find this very specific line or boundary in general, which is the largest which is at the largest distance from any of the classes. Okay, and then these two lines that basically define the borders. If you assume this to be the no man land here, then these are what we refer to as the support vectors, because these are the points that really do the heavy lifting in terms of defining the boundaries. You see the lines pass through them, and basically they are the ones that hold them in place. Okay, so this is the boundary line, and these two lines are the ones that basically define the margin area. Okay, so in terms of the different lines here, again, if you enumerate them, so if this line is 1, if this line is 2, well, this 2, and then this is 3, you see 1 and 3 are not that good because they are very close to either this class or this class, but 2 is right in the middle as far as possible from each of the classes there. So some highlights of support vector machines: it's the large margin classifier. It finds the optimum line that can separate. When I say line, we are talking about 2-class case here, or basically not 2-class. We are talking about 2-dimensional scenario, but there can be more dimensions. It's basically, line means just a boundary here. It finds the optimum boundary that can separate the classes, which will also be the line or the boundary that has the best generalizability. Right, if you're as far as away possible from the 2 classes, 2 data points there, then basically this large margin will also be the best generalizable scenario, meaning if new test points comes in, SVM will perform better than any line that does not fit this condition. Not all the data points influence optimally as in linear regression or naive Bayes, right? In those models, basically every point are taken into consideration. Here, the points that really affect the SVM boundary are the support vectors. And once they are found, actually, if you go back here, all these points can be even discarded. They are not needed anymore. And actually in the SVM, they will have like a weight value between 0 and 1, and these will be all 0 after the support vector boundary is found. They will be all 0. Only these points will have some score value, an alpha value. The curse of dimensionality when adding feature combinations has been mitigated by using kernels as transformers. We will see this soon, what we mean by that with the kernel SVM idea. So let's look at the first scenario here, the linearly separable SVM. We want to maximize the margin to closest positive and negative training samples, right? So these are the positive and negative examples here you see in the different colors. And then we want to find these parallel separating boundaries, so these 2 lines here. And these 2 lines are defined by the WXB is equal to 1, that's the upper line here, WX plus B is equal to -1. And the one in the middle is WX plus B, okay? So given the data points, we want to minimize this condition, and if we combine this into one, basically this is our condition that we need to satisfy. Okay, this is our objective, and this is the condition that we need to satisfy here. If the model can satisfy these conditions, then basically what this means, it will be able to find this boundary in the middle and these separating boundaries that touch the 2 classes there. So one thing, of course, here, it's a perfect scenario, it's perfectly separable. But what if there are data points that are, like this, from this category 2 class, class 2, if there's a point right here? And what about if there's a point from category 1 or class 1, if there's a point right here? What does the model do then? Then it becomes inseparable. The idea is if we add some tolerance to the model where it's still okay with these points, then then everything will be much easier to deal with. And that's what we call the slack variable. So the slack variable is defined as the distance to which point I goes beyond the boundary of its category, right? It goes to the other side basically, right? So you see this and this circle and this square are on the other side there. Slack variables allow some points not to be classified correctly to some extent. This is again related to maximal margin notion. That's always the main goal of the SVM models. It's not only classification accuracy. On top of classification accuracy, of course, it tries to get a good accuracy there, but also the main goal is to get this maximal margin idea. Okay, that's always the main goal of SVM. By sacrificing some accuracy, the SVM achieves a large margin, which benefits the overall problem. However, there is a trade-off between achieving a large margin and accuracy, right? Because if you do allow for some tolerance there, as you can see, the accuracy will decrease, right? There is a trade-off between there. The balance is found by penalizing the tolerance to errors in the cost function. So we do give some tolerance, but we also penalize that so that basically the accuracy doesn't drop too drastically, right? So this is the slack variable that we talked about. So that distance, these distances are basically the tolerance amount, right? That's the slack amount, and that's now incorporated into this condition here, right? Both the objective function has that now, so that's a penalty there. So we allow for some distance to be tolerated, but we give it some penalty as well. And then the condition also takes that slack variable into account now. So now the model tries to satisfy this, and the new SVM is called soft margin SVM. So the previous one, where everything was perfectly separable, it was called it's also called the hard margin SVM. So this one, where there's some tolerance included, this is called the soft margin SVM. So that's also you can refer to as the linearly separable case with misclassification, right? So if this is our scenario where the data points, we want to classify blue and green, if we just go with the hard margin case, then basically it tries to satisfy the condition where everything is correctly classified, and then there's still the large margin. So then, as you can see, this will be one side and this is the other side, right? But then if we apply soft margin, right, where we are okay with some tolerance, meaning we are okay with some misclassification to occur. But if we apply a very large C value, meaning if you apply a very large penalty value, then it will still be acting like very similar to the hard margin case, and it will still find this line, because a very large C means, although we are giving some tolerance or misclassification, that penalty is so large that the model basically cannot be okay with some misclassification because of the penalty being very large. And by the way, the C value, you will see it's one of the most important hyperparameters in SVM. It's one of the hyperparameters that needs to be tuned, and we can see the effect of applying small C values and large C values later on in our experiments. When we apply a low C value, meaning we are tolerant, meaning we are okay with some misclassification happen, and we are emphasizing the large margin more. So we want the large margin to be satisfied more than we are concerned with the accuracy. So then the model will find a line like so. So as you can see, this is misclassified over here. And then this is the large margin classifier. You can see the margin is much larger compared to this. Right, the large margins somewhere like this. This is much larger, as you can see. So what if the case of where basically it's nonlinear? Okay, so meaning even with the tolerance added, the slack variable, we are still not able to classify it and get a good SVM model. So for nonlinearly separable data, the SVMs work by mapping the input vectors into some high-dimensional feature space using nonlinear functions. The linear separation between two classes is done in this high-dimensional space. So we take the data from a low dimension to high dimension by introducing new, basically, variables. And then in that high-dimensional space, the SVM basically works in a linear way. So then it becomes a linear SVM in that higher space. But in the current space, it's basically what we see as a nonlinear separable, nonlinear SVM. The functions that perform these transformations are called kernel functions. So kernel functions basically serves the purpose of introducing new dimensions, but those dimensions are not actually included. They are just there for, the idea is there, but itself is not directly applied. So that's why we are not concerned with the curse of dimensionality. We can directly, apply these functions and work in a way, basically kind of a, this is also called like the SVM trick or the kernel trick, okay? So the idea of higher dimensions is there, but the higher dimensions themselves are not there. So that's why the curse of dimensionality is not a problem in this. And we are able to take it to higher dimension and get a linear model right there. So this is, several different types there are listed for the kernel functions. This is the Gaussian SVM, one of the most popular ones. This is the polynomial SVM. And there are a few other ones as well. So what I mean all by this talk is like this. So this is our scenario, the original feature space. We take it to a higher feature space, and then in that higher feature space, it becomes linearly separable, right? And then this SVM line is able to classify your data points correctly, okay? This transformation is what we refer as the kernel trick there, or the kernel transformation. So for example, you see here these data points in the current space, no matter what you do, you cannot, right? There's no line basically that can separate these data points. So then what can we do is basically, if we look at it from the side, let's say, these are the inner points, so they have smaller values. These are the outer points, they have larger values, right? Because the center is 0, 0. The center is 0, 0. So that's why if you take the square of each of the dimensions and add them up, and then create a new variable called z for that, right? The inner dimensions, the points in the inner circle will have smaller values, so their squares will also be small. So when you add them up, they will be at the bottom in the z dimension, the third dimension we are having now, right? And then the outer points in the outer circle will have larger values. Their squares will also be larger. So if you add them up, the z value will be larger. So that z is the third dimension. Now if you plot them, x here, y here, and z over here, x, there was only x and y before. So now with this added third dimension, you can see clearly that the purple points are at larger values, right? This is the z dimension here, and the yellow points have a lower values here. So a simple plane now will be able to separate them easily. So this is the idea of adding new dimensions to the model, and working with a model in this higher dimension where it's linearly separable in that case. As you can see in this higher dimension, it's linearly separable, right? But in the current dimension, it's basically nonlinear. So by adding new dimensions, we can get the linear separability in that new dimensional space, in that high dimensional space. It increases the accuracy. Computation will become slower, as you can imagine. And the question of curse of dimensionality should always be there, because we don't want too many new dimensions. It will make things worse. But as I said, in the kernel SVM, or by applying this kernel trick, the idea of higher dimensions is still valid, but it's not exactly applied. Instead, the kernel functions are used to directly get to the end solution. So what do I mean by this? So until now, it might not make much sense to you, but let's try to look at an example here. So let's say we have point A and point B, right? So basically there is 2 dimensions here in this scenario, right? So let's say this is point A, right, with A1 and A2 values, and point B, I don't know, somewhere B1 and B2 values, right? So this is, you can assume this is, the dimension 1, let's call this x1, and this is x2, right? So the A1, A2, B1, B2 are the values that the points have. Okay, so that's a1, a2, b1, b2. So this is our transformation, the phi function. Phi of a, if you transform it, it becomes like this. So we take this, we have a1 squared. So we take the square of this, we take the square of a2, and then what we will also do is we take square root of 2, we multiply that by a1 and a2. So basically, this is the transformation. This is the function it does. So every point as input gets into this phi function will be output in this manner. Okay, so it becomes a1 squared, square root of 2 times a1 and a2, and then a2 squared. So we have 3 dimensions here, right? We have 2 dimensions here, and then we have 3 dimensions here. Same thing for b, same output. So if we now multiply these 2 points, okay, so what we get is this: a1 squared times b1 squared plus 2, square root of 2 times square root of 2 becomes 2. So 2 times a1, a2, b1, b2, they are all multiplied, and then a2 squared and b2 squared. Okay, so this is when I say multiply, it's a dot multiplication there. Okay, so when I look at this, I can basically make it, what's the word for it? So simplify it, and it will look like a1 b1 plus a2 b2 squared, right? And when I also look at this, I can say a1 a2, right? Because this is basically a dot multiplication between 2 vectors. So a1 a2 transpose times b1 b2 squared, right? So in matrix notation there. So basically what we have is a1 a2 was the first point here, a, and b is the second point, b1 b2. So we have basically a times b squared, right? So, and why am I multiplying here? Well, because that's how like the SVMs work. If you I'm not really going into the detail of how the SVMs do the classification and their calculations, but basically what it does, it's basically we are multiplying the data points. So one of these points is the support vectors, and one of them is the new data point that we want to classify. So if you assume this a1 a2 to be the support vector there, right, and we said the support vectors play an important role, and this is the new data point, let's say, that's coming in, and we want to classify this. So what we will do is we multiply this data point with every support vector in the system. So this is one of the data points we have. All right, so that's why even after we do the transformation, we'll still multiply, right? This example basically shows that even after the transformation, if you are applying that multiplication, you're getting to the point where you can just initially take the 2 data points, a and b, and just multiply them and then square them. So we don't really need to go into this higher dimensional space in order to reach this solution here. We can directly take the points a and b, we can multiply them, we can take the square, and whatever the value we get, that's it. All right, so that's why, although the idea of introducing higher dimensions is there, the application itself doesn't introduce each of these new variables. Because if it were to do that, first of all, adding, it will need to calculate all these new variables, create a new vector, add it to the system. So all these requires time, it will be slow, and then multiplying these 2, as you can see, takes time, right? And doing all these things will take time. It might not matter for a single data point, but if you have, thousands of data points, it will matter, it will become much slower. So that's why this kernel trick makes this whole thing basically just as an idea, it is there, but it doesn't need to be applied. So we can directly go from here to here. All right, so this is the meaning of kernel trick. So from the previous slides, you have the primal, you have seen the objective. The objective functions there are referred to as the primal problem. So these are terms from the optimization of some, problems we have. Okay, and then we can also convert this into a dual problem. So in the dual problem, the problem will look like this. Okay, so the reason we normally we don't work with the primal but rather the dual problem is to make the solution much easier. That's the main reason there. Okay, Yeah, and finally, once the solution is found, so meaning what is the solution for a support vector machine? It's finding these alpha values. The alpha I values are basically greater than 0 for the support vectors, and they are equal to 0 for any other data point. So basically, that's why these support vectors will play a role in terms of classifying new data points coming in. The other points will not have any impact at all. So as you can see, the solution looks like this. So we have, once a new data point comes in, that's x. This is the support vector point. So we do the kernel function there between them. So the calculation example, something like this, right? So what I just shown here. And then we multiply that by the alpha value of the support vector of this current point I, and then the class label of that support vector as well. And the b is a bias term that's found during the process. So once you add this up, you do this for every support vector, you add them up. So basically, if it is, greater than 0, based on threshold, if it's greater than 0, it's one class. If not, it's the other class. That's how it works, right? And the labels here are +1 or -1. Yeah, and these alpha terms are also referred to as the dual coefficients. Okay. Yeah, and that's how the system works. So this kernel function here, basically, when it is a linear kernel, meaning we don't do anything fancy, but we just do the multiplication between the data points, that's a linear kernel, then it becomes a linear SVM problem. Okay, it's basically a dot multiplication between xi and x. But then if we take one of these kernel functions examples here, like this, for example, this is a polynomial kernel or the Gaussian kernel, then it becomes a kernel, what we refer to as the kernel SVM, which is more difficult and takes more time compared to a linear SVM. So we mentioned the parameters, the hyperparameters, right? So we are, choosing of the kernel is important. So do you want to work just with a simple linear kernel SVM, which is a linear SVM, which is, by the way, very similar to logistic regression in terms of its solution? Do we want to work with a polynomial kernel or an RBF? RBF stands for radial basis function, or the Gaussian kernel. These are the same things. We need to choose the penalty parameter and then the kernel specific parameters. So that will be, if we choose polynomial kernel, then we need to decide on the degree of the polynomial. If we choose a RBF kernel, then we need to decide on the gamma value. The gamma value and C are, both control the complexity of the model, with large values in either resulting in a more complex model. So that means the large values of gamma or C in both cases will result in a much more complex model, meaning the model will try to fit with much higher accuracy to the data points we have. Okay, so think when I say more complex, the overfitting will increase. All right, and we will soon see a nice example about this. The good settings for the two parameters are usually strongly correlated. Okay, so that's why C and gamma should be adjusted together, meaning when we do a grid search, let's say, we need to try to find a good solution for both of them at the same time. Okay, so let's take a look at the C value. So the C value is a trade-off between the complexity of the decision rule and the generalization error can be controlled by changing the parameter C. Okay, so it's a trade-off between the complexity, or basically the idea of the being large margin, and the error, the validation accuracy, the accuracy or the error of the model. So if you choose a higher C value, that means the error will decrease, at least the training accuracy will increase, or the training error will decrease. Okay, so training error will decrease if the large C value, but then the large margin will decrease, the margin will be smaller. So the C is a penalty term that determines how closely the model fits to the training data, right? It penalizes the misclassifications. And this also is the inverse of the regularization parameter. If we the regularization parameter is related to, like, for example, logistic regression or linear regression models, where it penalizes the coefficient values, right? So regularization would prevent large coefficients from happening, because large coefficients would mean overfitting. So there, the penalty value was being applied on the coefficient values. Here it's a bit different. Here's a bit different. So as you can see, it restricts the value of alpha, right? The alpha value is the value of the support vector points, right? So if you have a large C value, then you're okay with this alpha being larger. If you have a smaller C value, then you basically restrict it to be much smaller. And large C value would mean a large penalty on the misclassifications happening. All right, so decreasing C corresponds to more regularization. Okay, so right, you just see this notion here. So if you decrease this, then you basically increase the regularization amount, meaning you're restricting this alpha value from growing. Okay. So that's why if you think, maybe you can think these alpha values as like the coefficients of each of the support vector points. So here you're decreasing it, and then you're making it more restrictive, right? So it's the opposite of the logistic regression idea where you apply regularization. There, when you increase it, you're applying penalty on those coefficient terms, and then they cannot grow very much. Here it's the opposite. Here you're decreasing. If you decrease the C value, then you're making it more restrictive on the alpha values, which you can think of as the coefficients of each of the support vector points. So decreasing C corresponds to more regularization, restriction in the value of these support vectors. All right. So if you summarize this whole thing that I'm talking about, so we can say large C means large penalty, so increased cost of misclassification. Right, the model will be less tolerant to misclassifications. It will also mean smaller margin. It will mean, more complex model. And when you increase C, you are more, you're okay with alpha values increasing. So then large C will mean larger alpha values. So larger alpha values would mean more complexity, and basically that would mean less regularization. Okay. So regularization is about coefficients. Again, okay. So here the C value is controlling how much of a misclassification we are okay with. C value, that's why the term of regularization in logistic regression, and the C value here should not be confused. That's why I kind of stress that idea here. And I hope this slide would make it clear in terms of its of how SVM finds its parameters, these alpha values basically. Okay. Okay, so again, C value is an important hyperparameter to be found because it really affects the solution quite a bit. The other parameter that's important is the gamma parameter. This is related to Gaussian kernel. So when we apply the RBF kernel, the radial basis function, or the Gaussian kernel, same thing. We need to include the idea of tuning the gamma value. What it does, it basically controls the width of the Gaussian kernel. Gaussian kernel is basically like, you can think of a normal distribution. So if this is a support vector, so this will be the Gaussian that's being applied on, and gamma is the inverse of the sigma value. So if the sigma is basically standard deviation, then gamma is the inverse of this value. Okay. So it influences how much basically gamma defines how much of an influence a single training sample has. Right? So this is a single support vector. How much of an influence does it have? If it is a larger gamma, that would mean a smaller sigma value. A smaller sigma value would mean a much peak, drastic peak there, right? Like this. So if the gamma is larger, the closer other examples must be to be affected, right? If a new data point comes in, then if they are far away, they will not be affected because only these close points will be affected. But a smaller gamma value would be like this. right? So it will have a much larger sigma value. So then even the further away points will be affected, but of course, the amount they are affected is not too big, but they will still be affected by this. So the larger gamma means a small sigma or a high peak with small variation, and such a point, right, with a larger gamma will only affect those points that are close by. So this, again, you should think if you have much larger gamma, we have a much more complex model, and there will be overfitting if the gamma gets too large. And you can see all these things in this example here. So you see the effect of both C and gamma and how the boundary looks like. So when we have small C value and in a small gamma, you see kind of a linear SVM solution here. But if you increase the C value to 1000, as you can see on this image here, bottom left, you see a more complex model where it tries to get a higher accuracy, as you can see, right? So increasing C will increase the complexity of the model because now the misclassifications are penalized much more. All right. How is the effect of gamma? Let's take a look at that. So you have small gamma here. And when you go to the very right, you see a much larger gamma. So much larger gamma means a much small sigma value. So only those very close points will be affected. So that means overfitting. As you can see, we see now islands being formed, right? Because, these data points are very strong in its vicinity. So that means even a very single, like a support vector of one class will have its own basically area around it, right? That's why you see these islands forming up, because again, much larger gamma would mean very high peak. That means very, very strong effect of that support vector in its very close vicinity. So although it's very small area, it will have a large impact. So that's why you see these, like even these small islands happening. Now, of course, when both values are large, basically you are double overfitting in a way. So then definitely there will be islands happening like this. So these are not very good on the very right. So large gamma is not good. There's overfitting there. Maybe this is underfitting. Maybe it doesn't do a very good job. So something like this, as you can see, some like a smaller value of gamma or some smaller value of C, or combined in a up until a medium value is okay. Now, of course, I cannot really define what is small, what is medium here. That depends on the problem. That's why, doing a grid search on C and gamma is always advised. By default, I think C is 1 and gamma is 0.1 in general. So those might, provide a good starting point. But then again, it should be investigated and found by doing cross-validation, for example. All right, so we have come to the end. Let's take a quick look at how SVMs are in terms of pros and cons. So they are good classifiers in general, especially when the target variable is binary. It's okay when you have many features. That's a good positive side. But when you have too many rows, it can be very slow. And even like data sets of 100,000 rows, I have tried in the past. I have had trouble with in terms of its speed, so it can really get slow very fast, and that's mainly because of the multiplication between the data points, the matrix multiplication. That's one of the main reasons it gets so slow. So the support vector points are the points that affect the solution, the classification. So those are the most important points that we need to be aware of. So not every point is affecting the solution, so that's a good thing there. And with nonlinear, the kernel SVM basically is able to classify nonlinear model cases in a very high accuracy, so that's another good thing there. Again, outliers may affect the system or may not, depending on where they are located. So if they are already in the correct segment of the solution, they will have a minimal impact, maybe none at all, because they, as I said, in this SVM, the support vectors are the ones that really affect the solution. So any other point, no matter where they are, will not have any impact. And the linear SVM can be very quick, even on larger data sets, they should still work fine. So they can always be tried. They are simple to work with and they're quick in terms of its training. Yeah, as I said, one of the main cons is that when you have too many rows, it can get really slow. And the models themselves developed by SVM is not really interpretable. So compared to linear regression, and those kind of models, they are not very much explainable. And they're not very simple models as well. So other than the linear SVM, you cannot take them as base models. By the way, both classification and regression can be done. So generally the examples are based on classification because it's easier to work on them. But again, SVMs can also be used for regression as well, just like many other models. All right, so that's it. Thank you.